Woohoo! It is time for an introduction to calculus, the moment you've all been waiting for. We are going to take it to the limit, if you will, as limits will be involved. Anywho, let's get going. So, calculus. With these two fathers of calculus and their incredible hair. I just love the hair back then. I think I might grow mine out. Those are wigs. Anywho, so we have Mr. Bruss' distance from his house is modeled by that function d of t. We have a graph of it over there. While riding his bike to the store, he realizes he dropped his wallet and turns around to find it. After finding his wallet, he finishes his bike ride to the store. So let's take a look at this and what this graph really means. I feel like we look at graphs, we never really analyze them a whole lot. So over here on our y-axis, that's our distance we've traveled, right? Or that he has traveled on his bike ride. And then we have our time elapsed there for our t-axis. So at some point, he stops and turns around and goes backwards, like he backtracks. I think this would make sense. Maybe I should use a color that'll show up a little better here. This section right here, that would make sense for his backtracking, don't you think? Right, he's going back the other way for his distance, so he's like subtracting distance. But then he continues on and ends up at the store, right, as he was going to. Okay, so let's see here. What is his average rate of speed? Rate of change, or his average speed is rate of change, for his trip to the store if he arrives after 8 minutes. Well, it took him 8 minutes to travel a total distance of 1,300 meters. Okay, so we could do 1,300 divided by 8. That'd be our meters per minute, right? Let's go ahead and do that. And that gives me 162.5 meters per minute. Okay, cool. I like it. Simple enough, right? It's a little slow. So I took basically our starting point of 0, 0, and then our ending point over here of 8, 1,300, and found our slope formula. Change in y over change in x, rise over run. All right. Now it says, what is his average rate of change between 2 and 6 minutes? So now we're looking at a smaller point in time. So let's see here. 2 minutes right here, and then at 6 minutes, we're over here. So what's the average rate of change between those two spots? Now, we don't have exact values there, but we could maybe get a rough estimate, right? So let's see here. Our rise, we're going from what appears to be about what, maybe it's right about in the middle there, so something like that. And then let's see here, maybe that's about 2/3 of the way up, so that'd be about 800. All over, and then I'm going from 2 to 6. So this one, we get a negative 62.5. He is backtracking overall in this stretch. We could see like a little, if we were to connect these two, we do see a negative slope for our line, right? Okay, cool. And then what's his average rate of change between 2 and 3 minutes? So let's do that again. We've got I'll use a different color again. We'll use orange this time. So at 2 minutes and then 3 minutes would be right around up here. So this one looks like it's going to be a positive, right? Positive rate of change there. So we were at 1,050 for that first one. And the next one looks probably more like, let's go like 1,100. Again, these are rough estimates here. And then 2 minus 3. So I'd have negative 50 over negative 1, so 50. Okay. Again, rough estimates. These aren't exact numbers. We're just taking a look at the graph there and seeing the best we can do. All right. So here's an interesting question. Is it possible to know how fast he was going at an instant? Okay, so like at that exact split second of time, in this next part here it says at time equals 2. So at 2 minutes, exactly how fast was he going? Can we tell from this graph? Well, here's the issue. If I'm trying to find the slope at that rate of change, sorry, my chair is squeaky, that rate of change at 2, okay? And if we think about our slope formula, it's rise over run, or change in y over change in x, right? So we would do, let's write down slope formula. So here's one version, let's say, of this slope formula. So if I were to take that time of 2, okay, and I were to plug this in. So let's say I wanted to do f of 2, but I wanted exactly at that point, I'd have to plug in 2 again, because I don't have any other point, right? I'm trying to find it just at that point, not over the course of 2 points. And then I'd have 2 minus 2, but 2 minus 2 is 0, and the function evaluated at the same point minus the function evaluated at that point as well, it's going to be 0 divided by 0. Boom, mind exploding, right? That doesn't work. And more about that later, but we can't really figure it out in that way. But what if, hear me out here, what if I were to go with this? Instead of 2, what about a point like really, really close to it? Let's say 1.9 or 999. We could go with a whole bunch of 9s, right? And then I'd have to do minus 1.9. I did the same thing. I got 5 9s, 5 9ers there. Well, now, although this isn't going to be exact, it's going to be really, really close. And if I were to do that, say I were to evaluate it like this, and then I were to evaluate it again, even closer, and then again, even closer, and then again, even closer, and then again, even closer yet, perhaps I could start to see what that slope is looking like what number it's approaching. The closer and closer I get of determining that slope, then I'm going to get this number, and perhaps I can make a good prediction as to what that number might be, what that slope might be. So this right here would be how I'd calculate to give a close estimate of that instantaneous rate of change at 2. Again, it's not exact, but the closer I get with my x values to that 2, the more accurate it's going to be, or the closer to that actual slope it's going to be. Now, give a rough estimate of the instantaneous rate of change at 2. Let's see if we can figure that out. So, or at least give a rough estimate, as it says. If I throw this point on 2 here, and I want to get the slope, you may have heard this word before called tangent, right? Yes? Not necessarily with like trig, like with the function, but a tangent line resting on that one point, okay? If you were to see this curve and you were to take, like, say, a 2x4 and rest it on that point, that would be tangent to it at that point. It's only touching that point. So this line right here would be tangent to it and could give me a good indicator as to my slope. So let's see if we can estimate here. If I'm looking at where it crosses the x-axis there, that's probably about like, what, 800? And then it rises up to about, we said about 1050. So 800 to 1050, 1050. And I go from 0 to 2. So we're going to have 250, negative 250 over negative 2, or 125 is our rough estimate. Okay? And with fancy technology, check this out. I think I could do, I could take this guy, yep, I can move it and position it. Ooh, look at that. I can move it around and maybe get a better idea of that. That's even right there. If I move it, kind of like we're talking like vectors and stuff like that, position it at 0, 0. Now I can actually see that my tangent line looks more like a rise of 300 and over 2, so maybe even 150. Maybe that's a better estimate, you know? Isn't that fun when math is like, well, I don't know what the right answer is. Perhaps it's this, maybe it's that. But in any event, what we're trying to do is we're trying to see what is that rate of change at that exact point. Okay? And that, my friends, will be developed more in calculus there. So exciting. So exciting. Let's continue. Enough babbling about this one. So a totally different style problem here. This is B of T represents the buffalo population in the United States, where T is measured in years since 1800. Okay? Lots of buffaloes back in the day. What does B of 90 represent is the question. Well, that would mean that that's the number of buffaloes present in 1890, right? If I plug 90 in, evaluate at the function, the output there would be the number of buffaloes that are present in 1890. So there we go. Buffalo population in 1890. Awesome. All right, next one. What does B of 50 minus B of 0 divided by 50 minus 0 represent? So that's our slope formula, right? It's our rate of change. So this would be the average rate of change, average rate of change in the buffalo population from 1800 to 1850. There we go. So that's how much the average rate of change of buffalo population. Cool. And then what does B of 32 minus B of 31.999 over 32 minus 31.999 represent? So this would be an estimate for the instantaneous rate of change of the buffalo population in 1832. And boom, there we have it. Again, this is an estimate for it. And as we pick points that are closer and closer and closer to 32 in this particular example, the more accurate it will be. And if we continue to, say, evaluate this further and further out with all those nines, right? More and more and more nines at closer and closer to 32, we might see a pattern. We might see a number that it's approaching. And that, my friends, we'll look into more with the limits. There's just so much out there that I can't tell you right now. It's like a good movie, right? I don't want to spoil it. All right, that's it for this video. America, freedom, rock and roll, Costco, Yo-Ro, Riverdog, James Graham. Deuces.